Today I would like to discuss with you some of the advantages and functions of read-only storage as it is utilized in System 360. First of all, I think we need to look at the two primary purposes or reasons for read-only storage. Number one, all systems require a control function in order to make the data flow through the system on a balanced operation to give us the best price performance. And read-only storage now replaces the conventional tubes, SMS cards, various other types of circuitry that we've utilized in the past. Number two, it gives us compatibility control with proven object programs of the 1400 and 7000 series systems so that we can ease the transition from currently installed 1400 7000s to System 360. I think you should note that the Model 70 uses conventional circuits for the control of its central processor unit and associated equipment due to the speeds involved at that level of machine. Now, by way of illustration, we will use an example of the read-only storage that we find in the Model 30. And in this, I simply want to say that the read-only storage replaces all types of tubes, wiring, resistors, capacitors, etc., and puts in a non-write, non-destructive read-only memory. This is not available to the application programmer, you yourself for instance. It is utilized only by the engineer who is actually developing the internal program for the machine. We'll introduce a few terms such as micro-instruction, micro-programming, and as we go through the explanation, I think this will all become clear to you. Now, first of all, in the control of a system, we are concerned with 5 elements: input of data, output of data, storage for the containing of intermediate results of data, and the application program and the programming systems, whatever may be resident there, the central processor unit with its arithmetic and logical units, and of course the control function which ties all of these together and maintains a smooth flow of data through the system. Now, by way of illustration of the program cards that are used in this machine system, this is a standard 80-column size card. It has 12 microwords corresponding to the 12 horizontal rows that you normally find on a card of 12 through 0-digit values. It has a series of capacitive plates on here such that this can form, when it's put in the sense plate, what we call the card capacitor read-only storage. Until such time that an engineer determines that a pattern of these little plates needs to be punched out, I would look at this just as you would look at a coding sheet for a program as my blank program card. The micro-instruction involved in this is the internal instruction that the machine will use for decoding the add or the move or the read or the write instruction that you give it in your application program. Internally, the machine looks at that instruction, say an add instruction, as a macro instruction. And then it goes into a micro level or several individual steps of instructions such that we can now make the machine move the data through this machine, develop the desired results, and put the answer or the results in the specified locations. Any single instruction may require one or more of these micro-instruction levels. It's strictly dependent on the complexity of the operation that you're trying to perform. In the case of the Model 30, the engineer determines a bit pattern for each micro-instruction word, and these bit patterns are sensed and sent out through this sense board into the machine such that they will cause various circuits to gate, open or close to allow the transition of data or the movement of data through the machine. Read-only storage also takes care of the problem of getting timed impulses through the proper circuits at the proper time, under control of the bit pattern. Now, just as in normal core storage, which is a destructive type of readout storage, we have a parity associated with each micro-instruction. so that every time we read a bit pattern out of here, we know that the machine will function in a reliable and valid fashion. Now, to form a read-only capacitive storage device in here, we have established between the sense board and this program card a series of capacitors. Each of the little squares that you see detailed on here forms one plate of a capacitor. And any time you take two plates, put them close together and apply a voltage across them, you can develop a capacitive pulse. If we have a pulse there, we say that we have a bit, or a 1 condition. If I perforate one of the plates or remove it, then I say I have a no bit or a no capacitive pulse. Consequently, we are able to develop the 0-1 binary bit pattern required for the machine operation. The engineer determines what pattern he needs at a particular sequence in time of the machine operation and sets this up in the cards. That then becomes a permanent read-only storage that the machine will constantly utilize. And it remains fixed until such time that the engineer comes along and says he has to change it or modify it to improve some operation, or to change the method of operation, or to add a feature to the system. Now, for a moment, I'd like to illustrate to you some of the other read-only storage devices that are used in the Model 40, the 50, the 60, and the 62 to contain the microinstruction. Here again you see an example of the Model 30 read-only storage microinstruction program card that the engineer develops. And you can see here a bit pattern as indicated by the white background. At the proper time, each word is accessed into the encoding and decoding circuits, and then the timed impulses are sent out to gate the machine. In the case of the Model 40, which was developed in Hursley, England, the engineers were going to develop a read-only storage device, but they were told that the only prime criteria that they had to follow were two things. One, all programs had to be functionally compatible so that we could have upward and downward capability for the instruction sets of System 360. And we could take a program for the Model 40 and run it equally well on the 30 or equally well on the 50, getting the same valid results. In the case of the Model 40, the engineers developed what we call a transformer read-only storage. I'm sure most of you are familiar with transformer action. You induce a current in a primary coil. This develops a field around the coil, and if you have a core running through that, you can then develop a secondary pulse in a secondary winding. And here again, if we have the presence of a transformer pulse, we have a 1 bit. If we don't have the impulse, then we have a 0 bit. So we have again the 0-1 binary bit pattern required. In the case of the Model 40, a microinstruction word is comprised of 60-bit positions. The outside row forms one word, the inside row forms another word. So each of the tapes in a Model 40 has 2 microwords. Each of the cards in a Model 30 has 12 microwords. In the case of the Model 50, 60, and 62, due to the speed circuits involved and the complexity of the circuits, they went to still another type of read-only storage media. And this is an etch plate with, again, a similar electrical phenomena as used in the 30, a capacitive effect. And now the bit sizes for each of the word varies depending on whether you're talking about a Model 50 or 6062. And the number of words will vary depending on, again, the work that you wish to accomplish within the machine circuits. So the 3 different types of read-only storage all accomplish the same function, the control of the System 360 processing system that you would have in any one installation. It also is consistent in that all 50s have the same pattern of read-only storage, all 40s have the same pattern, and all 30s have the same pattern, as again do the Model 60s and 62s. All right, from the read-only storage control then, I would like to simply go through a very simple example of add A to B and store the result in C with a representative data flow and a representative example of microprogrammed instruction. It's very basic, but I think it will help give you a better understanding of read-only storage. In the chart that we have here on the wall, we'll say that this will represent the data flow of a system, and that we have main storage. We have a storage address register so that we can always control the point or location within storage that we're accessing. We'll have various registers in here that will store data and hold them intermediate. We'll have an A and a B register or an X and Y register or a P and Q register, whatever terminology you wish to use, associated with the arithmetic and logical unit. And of course we'll have a sum register in this case to get our results back into main storage. Now, a very simple basic data flow, but how are we going to control it? We take a look, we can say that this might be a representative micro instruction routine to handle the simple single instruction that as an application programmer you would write for System 360. And that is, let's say, add A to B and store the result in C. And I've used basically the illustration of the Model 30 micro programming. Under our read-only storage address control register, again, we need to know at all times exactly where our next instruction is coming from, so we can sequence through a fixed routine, or under certain conditional branches we can leave a routine and go to some other micro instruction. So we have the same type of programming flexibility from the engineering side that you have in your application program for handling your data. Let's say that at point 0 we will start out with step number 1. We just accessed a new instruction from core storage and we are starting to decode it. Our micro instruction at this time tells us that we want to read A field out of storage. In order to do that, we've got to either close or open certain gates. In this case, we send out a timed impulse which is going to take us up to gate 1 and close that, and then as our sensing pulses come through storage at the proper point, we will transfer the data field A into the storage register. At the completion of this micro level instruction, we then advance to the next sequence instruction under control of ROS address register, and we see that the next signal or instruction we get is to regenerate the A field. Remember, we came out of a destructive readout device. So in this case then we close gate A and send timed impulses representing the data that we just took out of core storage and send it back to its original location. Then the next thing that we want to do on the next logical sequence of instruction is to store A field, in which case again we've got to close another data path. So gate number 2 is closed and we put this into a hold register. The read-only storage control then advances to the next sequential instruction, which says in this case read the B field. So again, under control of the timed impulses coming out, we're going to close gate number 1, come out here to main storage and take the B field in. It will hold there because there's no other place for it to go. Again, under read-only storage address control register, it says go to the next sequential instruction, and there we see a multiple function being carried out on this single instruction step, and that in this case is simply adding A to B. So we had the A field held here, we had the B field in here. So to execute this, we will close gates 3 and 5, moving the A field here, the B field here, and since we are now tied directly to the arithmetic logical unit, the rest of the function of the arithmetic operation is carried out directly, developing the sum and leaving the result in the arithmetic and logical unit. Then the next micro instruction says that we want to store the sum. In this case then again we must close another data path, and as you can see by our timed sequence here, we will come out and close gate number 4, at which time the sum comes over here. Now we want to take the sum into main storage. We could just as well say store this register. In this particular case we'll use the term regenerate the sum into core storage, and this is simply to illustrate that we're going to use a common data path that we had used previously for the A field. So we will take the value, which is the result C, bring it out, and put it in its appropriate location under control of the storage address register. That's a very basic example of how read-only storage functions, but I believe that it gives you the idea that all of the data flowing through the system has to go through under a sequenced and properly timed control, and we do that with read-only storage. Now this points out the fact that it is and can be extremely flexible, so that for any conditions that you would have, the engineer can come along and handle overflows, underflows. He can handle balance, rather compare, equal, high, low, and select the appropriate internal control to branch to the next course of action. Now, that pretty much addresses read-only storage as we see it within the system. In the case of the Model 30, with this device, several of these sense plates would be in the machine such that the unit is actually approximately this wide and has approximately 4,000 words of read-only storage used. That takes care of the 360 instruction set, or what we call the native 360 mode of operation. So anytime I have object code for the 360, I would use this read-only storage device. Now, that is true if I'm talking about a Model 40. I would have a read-only storage unit. In this case, it would be the transformer read-only storage type of unit. If it were a Model 50, 60, or 62, it would be the other type of read-only storage as we see indicated here. That is the balanced capacitor type. Now, let's get to the second major advantage of read-only storage, and that is the compatibility feature and capability that it allows us. To run a machine in compatibility mode, we would in effect set aside the normal read-only storage with a 360 instruction set. That's fixed. The engineer determines that, and it stays that way from time here on out until such time that he generates a change. The application programmer never can affect that. Now, I have a Model 30 or a Model 40 or 50 or 60, and I have a certain machine that I want to run in what we call the compatibility mode. I will specify that feature on my system, and then in addition to the read-only storage, which contains the 360 instruction set, I will get another unit that will be added to the machine. So we'll assume the 360 read-only storage is here, and this is a new one. Now, the only difference between the original read-only storage and this one is that the code that is generated in this read-only storage does not interpret 360 instructions. It now interprets 1401 instructions, or 1460, or 1410, or any of the 7000 series that we run under the compatibility mode. In which case, then, we're saying that for compatibility operation, I would use this type of read-only storage, for instance, in the Model 30. I would go through the same type of operation, but the commonness in here now comes back to the fact that I use the 360 data flow paths. I don't add new data flows. I don't put in a 1401 internal circuit. I make the 360 look like a 1401, for instance. But I do put in a new read-only storage so that I can properly sequence and control the flow of data through the system. All right, in the case of each of the models that we're talking about, we must then have some read-only storage if we are going to use read-only storage in what we call the compatibility mode. Now, I would like to go on to a few definitions and then give you some significant advantages of System 360 and read-only storage. Again, by way of very brief summary, the primary purpose is the control of a system, in this case, any of the models 30 through 62. Secondly, it does allow us to interpret an instruction set for another machine, and as we have specified, those that have been announced as compatibility features. I think one of the most difficult things that in the marketplace that you have is a handling of the terms that you will run into. Compatibility, as we look at it, normally means that the instruction set, let's say for 1401 on the Model 30, is comprised of all read-only storage with a microprogrammed instruction, as we talked about, and additional SLT circuits. No programming support is normally involved with that. That is a hardware compatibility feature. The second term we run into, although you will find it listed in your sales manual as a compatibility feature, is the term emulation. And that means that we will use from very much read-only storage to relatively little read-only storage, from very much SLT additional circuits to very few additional SLT circuits, and to simple input-output programming support to very significant comprehensive programming support packages. And in the case of pure simulation, that's a term that you're all familiar with because we've had it since the age of computers, and that is that we will interpret any instruction set from another machine and try and make the host machine act as though it were that foreign machine. And that is all done by interpretive routines in software only. Now, I think the next thing that we would like to discuss are the advantages of read-only storage. Primarily, read-only storage allows a full instruction set for the models 30 to 62 so that you can have true upward and downward program compatibility of your programs. And also, it says that regardless of what model I am on, I have one set of instructions to learn, and I'm going to use one set of programming support. It provides the best system price performance because now we find that through the use of read-only storage and the different types that I've indicated here, we are able to allow a full instruction set performance on a small machine, which is balanced to its throughput performance, as well as allowing a very comprehensive system like the Model 60, 62, with its full instruction set identical to the 30, matched to its throughput performance. One logical design of System 360 through read-only storage control. This basically is a way that we obtained the one logical design, although we actually have 6 physical systems involved. It's the key to program compatibility upward and downward, as I've pointed out. A very necessary requisite for expanding and shrinking workload situations. Then the second, I think, most important advantage that I've highlighted already is that it does provide compatibility with proven object programs of the 1400 and 7000 series as specified on the compatibility features that have been announced. Each microprogram instruction has parity to validate the read-only operation. And again, let me point out this is read-only. Nobody can write into this memory. 7, it will definitely facilitate field engineering improvements. And when I say field engineering improvements, the product department or division develops the engineering updating of the machine, and it must be installed by the field engineering. Due to the flexibility of read-only storage, the relative ease of replacing sections of it, we are able to generally speed up the engineering improvement of a system with a greater reliability. It reduces the CPU requirement for the control function of the computer, and in some cases has reduced it as much as 4 to 1. All right, at this time, I would like to show you a series of slides which will give you, again, a somewhat detailed summary or brief summary of what I've discussed, and also will illustrate how some of these devices are physically located within the equipment. Here we see an example of System 360 circuits as we might have it with conventional control, for instance in the Model 70. The local store, which contains various registers, your arithmetic registers, the ALU unit, and the shifter. Now all of these units have to be gated and controlled so that data will flow through them properly and at the correct time. We do that with timed circuit impulses over here with logic control as we see it associated in these units. Now in the case of the Model 70, this is extensive SLT circuitry. But in the case of the smaller systems, the same type of control in order to give us this control over the data flow and to handle the instruction set would put us out of proper bounds as far as a good price performance. So then we go to read-only storage. The logical function is still there in that we still must gate the registers and control the data flow, but we have simply replaced all of the SLT circuits with smaller or lesser amount of SLT and read-only storage units with the permanently microprogrammed instruction set. Here again we see an exploded view of the type of microprogrammed card capacitor read-only storage as is found in the Model 30. This unit happens to be the sense board. This is an example of the microprogrammed card itself. Here is a view of a full module of read-only storage for the Model 30. It happens to represent approximately 4,000 words, and here you see a separate microprogrammed card. You can see the ease in the case of the Model 30 of inserting microprogrammed cards or changing microprogram instructions. It's very necessary, of course, that you recognize that each set of micro instructions have a very finite and fixed sequence relationship to the total program, and as such, nobody but the qualified and designated field engineer should be doing any manipulation of these cards. Here you see it actually mounted within the CPU of the Model 30. It's not a very large unit, relatively small. Here again pointing up the CPU size reduction that I addressed earlier, in some cases as much as 4:1. This is an example again of the transformer read-only storage micro instruction mylar tape, and here again if you look closely you can see the circuit lines that come down and the little perforations in here which tell us that a current will go around a core or will bypass a core, thereby developing the bit no bit condition. This, as I said, has 2 micro words for the read-only storage instruction set. Here is a little bit better view of an individual micro instruction tape. Here is the type of core that is inserted through several of these tapes in a complete assembly, as we see this set of tapes fanned out from this unit. All of the tapes have contacts that are plugged in down here, and then they go into the logic circuits and tie into the rest of the data flow of the system. This is an example of the bit plane for the balanced capacitor read-only store that we find in the case of the models 50, 60, and 62. They all use basically the same type of storage. Again, as I said, the word size varies depending on what model we're talking about. But you can see the way that the field engineer can change a bit plane in these units. This is known as a spider, and that's used to press all of the bit planes in a particular unit of read-only storage together so that all elements of the micro instruction word in there, that is all the capacitive elements, maintain the same electrical phenomena capacitance value. Here is a picture of the thing as it might fit in there after the engineer has actually inserted it onto the location pins. Here is a standoff view in the case, this particular case, of a Model 50, where you can see all of the read-only storage involved. This is only a couple of thousand words, but as I explained to you, the bit planes that are used have very large micro-word instructions involved in it. The elements that you see down here are the large circuit boards where SLT circuits are involved. This is an exploded view or back-off view of the Model 60, and in this case the read-only storage happens to be located in this part of the CPU. Somewhat different as far as its physical location between the Model 50 and the Model 60, but its function is identical to the Model 50. That is to handle the interpretation of 360 instruction set. By way of summary, these are the announced compatibility features. I should mention at this time that we have since announced the 1620 emulator to go on to the Model 30. In the case of the Model 30, until recent announcement of the program mode switch, all of the Model 30 emulators were what we call true hardware compatibility features. In the case of the Model 40, we are in the emulation mode as we are with the 50s and the 60s and 62 systems. I trust that these slides and the other presentations in here have served to illustrate to you the function and better define read-only storage as it is utilized in System 360. Thank you very much.
A member of the audience has been given the responsibility for answering any questions you may have regarding this presentation.